Hello everyone, welcome to Vihari Academy. This is Dr. Rekha Piliyadigula, researcher by profession. So today we are going to learn about the position vector and how to write it in vectoral form using the coordinates and how to get its magnitude. And also we will be discussing about source point and field point and the vectoral transformation with respect to the coordinate transformation. So first let us see what is a position vector. So this is the three-dimensional Cartesian coordinate system with axis labels as x, y and z, having the unit vectors as I cap, j cap and k cap pointing towards all three axes. So now let us say we have a point P here with coordinates x, y and z. So it is just a point or a location in the three-dimensional space which is defined by these three axes. And here will be the origin of the Cartesian coordinate system, and the line that draws or starts from the origin to that point is called a position vector, and this position vector always points towards, radially outward from the point. So let me call this position vector as R or bar. So we can write this position vector as xi cap plus yj cap plus zk cap. And to find out its magnitude, we represent the magnitude as modulus of the vector. It will be square of sum of squares of all the vectoral components. That means x square plus y square plus z square. If we want to quantify the direction of this position vector, then we need to know the unit vector. To find out its unit vector, this is the notation to represent the unit vector along this direction, and we have to divide this vector with its own magnitude. Then the resultant will be the unit vector pointing towards the direction of the position vector. This will be xi cap yj cap plus zk cap divided by its magnitude, x square plus y square plus z square. This gives the direction unit vector of this position vector. So now we know how to write vectoral component of a point and how to calculate its magnitude and how we can define its unit vector. So now, very often in electrodynamics, when we discuss most of the topics in electrodynamics, we need to have two concepts. That is, one is source, another one is test point or field point. So in a more general sense, we can call it as a field point. So one source point will be there where one charge will be kept, and this is the test point where we keep the test charge to identify few field parameters imposed by this source charge. So in this way, we need to know the concepts of source charge and field charge. So if in case this is the source point, this will be the position vector of this source point. And for this field point, this will be the position vector of the field point here. So the line drawing or the line combining these 2 points will be the separation, and if you write its components in the form of a vector, we can call it as a separation vector. Let me take this as the source point and this as the field point. So now we have covered what does it mean by source point, field point, and what is the meaning of separation vector. So now we will quantitatively define them. Let me take this as the source point defined by r prime, and this as the field point defined by r. So this will be the position vector of source point, which can be defined as r prime over bar, and this will be the position vector of the field point r bar. So now we are going to define this separation vector between source point and field point. Say for example, r prime's coordinates are x prime, y prime, and z prime, and if the coordinates of field point are x, y, z, this separation vector I would love to call it as r bar. Then let us define r bar in vectoral form, which is the separation vector between source point and field point. How can you do that? You can get the separation vector by subtracting the source position vector from the field position vector, that is r prime bar minus r bar. This is nothing but x prime minus x along x direction plus y prime minus y direction and z prime minus z along z direction. So now to know its direction, we have to get the unit vector corresponding to this separation vector. Then let me write the magnitude first. This will be square root of x prime minus x square, y prime minus y square, z prime minus z square. This is the magnitude, and now the unit vector can be represented as r capital R cap, which is nothing but r bar by modulus of r divided by its magnitude. This is the position vector corresponding to the separation vector between source point and field point. And now let us talk about vectoral transformation when the whole coordinate system is transformed from its initial position. Let us take a three-dimensional Cartesian coordinate system labeled with x, y, and z, and say for example we have a point A with coordinates ax, ay, and az, and we love to call the position vector as a bar. So, to discuss the transformation concept, let us simplify the system so that we are keeping x as the constant. That means x will be the axis of rotation, and y and z if they are rotated about this x-axis with an angle phi. So now let us discuss about the new coordinate system that is formed by rotating the previous Cartesian coordinate system with an angle phi from its previous position. Say for example, this is the angle that this position vector is making with y-axis. Then how we can write its components? So as we are keeping x as the constant, we will be focusing on the y component of the vector and z component of the vector. Y component of the vector will be ay and z component will be az. So ay you can write it as a cos theta because it's making an angle theta with y-axis, and az will be a sin theta. So now just imagine that the y-axis is rotated, both y and z axis are rotated from their initial position with an angle phi. And let us suppose that the y component of the vector Ea bar will be now Ay bar, just to differentiate both the old and new components of the vector. I'm just putting a bar over the element. So Ay bar will be whole system, the whole coordinate system is rotated. The new angle will be theta bar, which is theta minus phi. So this will be the new angle. And the z component, new z component, can be written as a sine theta bar, which is again a sine of theta minus phi. So now let us completely define them. Let us split this term and we'll see how will be the end result can be linked with the old coordinates. So we have Ay bar as a cos of theta minus phi and Az bar as a sine of theta minus phi. Let me quickly elaborate this term of cos A cos B plus sin A sin B. In this sense, we can elaborate this term of Ay bar as A of cos theta cos phi plus sin theta sin phi. So now let us split it. A cos theta cos phi, A sin theta sin phi. We know that A cos theta is nothing but Ay, that is the old coordinate of y component of the vector A, and A sin theta is the Az. So we can replace the terms, and finally we can get Ay bar as Ay cos phi plus Az sin phi. This is the relation between the old coordinates and new coordinates of the Cartesian coordinate system when it is being rotated about x-axis. So now we'll write down the term, the same kind of term. So this is the relation between old and new coordinates of A bar. So now just let me put them all together into a matrix form. So these are the new coordinates and these are the old coordinates. Here comes the transformation matrix corresponding to the transformation that happened. First, let us write AY components. Cos phi, and here comes sin phi, which is the coefficient of AZ for AY bar. And then here comes coefficient of AY is minus sin phi, and here is the cos phi. And this is when y and z axis are rotated with respect to x. If in case the whole system of Cartesian coordinate system is rotated with an angle phi, then we have to extend another term here. We will get 3 by 3 transformation matrix. These are the new coordinates and these are the old coordinates. In the case of rotation happened for 3 coordinates, I mean 3 axes, we may have to write ax bar, ay bar and az bar, which will be the new components of the vector a bar, and here comes the transformation matrix, and here will be the old coordinates, and here let me write it as an OR matrix, R xx, R xy, xz, then RYX, RYY, RYZ, RZX, RZY, and RZZ. Having this in mind, let me write it in a more compact way by using algebraic equation for each coordinate or each component of the vector. Let us take this is the AI. This is the component of our interest. It may be AX bar, AY bar, and AZ bar, anything. And let me take another variable Z, which loops from 1 to 3. Each number is for each axis. 1 is for x-axis, 2 is for y-axis, and 3 is for z-axis. Here comes the term Rij and the old coordinate. This is the most compact way of representing this transformation. And in the next session, we are going to talk about del operator, and with this del operator we can form divergence, gradient, and curve. So in next session we will cover these three. Thank you.